The directions say to find the limit, and we can apply L'Hopital's rule if needed in these examples. Let's take a look at example 1. Suppose we have the limit as x goes to 3 of x minus 3 divided by x squared minus 9. So this is equal to the limit as x goes to 3 of 1 times x minus 3 divided by x plus 3 times x minus 3. That's how we factor x squared minus 9. Now remember, x is getting closer and closer and closer to 3. X does not equal 3. And so from here, what we can do is cross off the x minus 3's. Because remember, x minus 3 divided by x minus 3 is equal to 1 as long as x does not equal 3. Okay? And so this is equal to the limit as x goes to 3 of 1 divided by x plus 3. And by direct substitution, we get 1 over 3 plus 3, which is equal to 1/6. And so therefore, the limit as x goes to 3 of x minus 3 divided by x squared minus 9 is equal to 1/6. And that's example 1. Let's take a look at example 2. Suppose I had the limit as x goes to 4 of x squared minus 2x minus 8 divided by x minus 4. And so when I look at that numerator, I notice that I can factor that numerator. And so that's what I plan to do. So this is the limit as x goes to 4 of. In the denominator, if you don't mind, I'm going to write this as 1 times x minus 4. In the numerator, I'm going to write x minus 4 times x plus 2. And just like in this last example, we can cross off the x minus 4's. Now, you might ask why, and I'll do this down below. X minus 4 divided by x minus 4 is equal to 1 as long as x does not equal 4. And remember, when you multiply by 1, when you take an expression and multiply by 1, the value doesn't change. Okay? And we're taking a limit, so x is approaching 4, x doesn't equal 4. And so this is the limit as x goes to 4 of x plus 2. And by direct substitution, I'm going to replace x with 4 and get 4 plus 2, which is equal to 6. And so, therefore, the limit as x goes to 4 of x squared minus 2x minus 8 divided by x minus 4 is equal to 6. And that's example 2. Let's take a look at example 3. Suppose we had the following. Suppose we have the limit as x goes to 1 of x cubed minus 2x squared plus 1 divided by x cubed minus 1. Okay? Now, if we go the factoring route, it does take a bit of work, but it can be done. Okay? And in fact, I think it would be more productive to show you how to do that. And so this is how it works. Now, recall, a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So if I take x cubed minus 1 cubed, this is equal to x minus 1 times square the first term, so I get x squared, multiply the x and the 1 together and change the sign. So I get plus x times 1 plus, and then I'm going to square the last term, which gives me 1. And so here, I'm going to get the limit as x goes to 1 of. In the denominator, I get x minus 1 times x squared plus x plus 1. Okay. Now we need to take a look at the numerator. Now, there's a couple ways you can go about this. All right? Now, I would attack it this way. It's tricky, but I'm going to take x cubed minus 2x squared plus 1. And I'm going to write this as x cubed minus 2x squared plus 2 minus 1. Okay? And so now what I have is a 4-term polynomial. Of course, it's not reduced, right? I have 4 terms. But what I'm going to do is I'm going to write this as x cubed minus 1. And then I'm going to write minus 2x squared plus 2. Now, what I want to do is I want to look at these first 2 terms. And that's a difference of cubes. Okay? And so this is x minus 1 times x squared plus x plus 1. We just did it right here. And then I want to look at the second 2 terms. And I'm going to factor out a negative 2. And when I do that, I get x squared minus 1. Okay? But x squared minus 1 can be factored. And so this is x minus 1 times x squared plus x plus 1 minus 2 times x minus 1 times x plus 1. Okay. And so notice how there's an x minus 1 common to both, and I'm going to pull that out. And when I do, I get x squared plus x plus 1 minus 2 times x plus 1. Little lengthy, but I think worth it. And so this is x minus 1 times. Now, I'm going to get x squared plus x minus 2x is minus x. Plus 1 minus 2 is minus 1. So it should look just like this. So in the numerator, I get x minus 1 times x squared minus x minus 1. It's a really nice way to factor when you have something like this. Now, notice how the x minus 1s go, right? We can cross those off. And what I get is the limit as x goes to 1 of. I get x squared minus x minus 1 in the numerator. I get x squared plus x plus 1 in the denominator. And I'm going to go to the next page, maybe the next page after that. And so the limit as x goes to 1 of x squared minus x minus 1 divided by x squared, and we can remind ourselves, plus x plus 1. We get 1 minus 1 minus 1 divided by 1 plus 1 plus 1. And so this is negative 1/3. It's a great question. And so therefore, the limit as x goes to 1 of, and I get x cubed minus 2x squared plus 1 divided by x cubed minus 1 is negative 1/3. And that's example 3. Let's take a look at example 4. This one's a little more classic. Suppose we have the limit as x goes to 0 of, we'll do this one. So we get x squared divided by 1 minus cosine x. Now, x squared approaches 0, and 1 minus cosine x approaches 0 as x approaches 0. And so this is of the form 0 over 0. And so we're going to apply L'Hopital's rule on the next line. And so this is equal to the limit as x goes to 0 of. Now, when I differentiate the numerator, I get 2x. When I differentiate the denominator, I get sine x. Okay? Now, we've learned, we could note this over here. We've shown that the limit as x goes to 0 of x over sine of x is equal to 1. We've shown that. And so I'm going to pull the 2 out in front. So I get twice the limit as x goes to 0 of x over sine of x. But this is equal to 2 times 1, which is equal to 2. And so, therefore, the limit as x goes to 0 of x squared over 1 minus cosine x is equal to 2. That's example 4. Let's take a look at example 5. Suppose I'm given the following. Suppose I have the limit as t approaches 0 of 8 to the t minus 5 to the t divided by t. Now, t approaches 0, and 8 to the t minus 5 to the t approaches 0 as t approaches 0. And so this is of the form 0 over 0. And so we're going to apply L'Hopital's rule here. It's the perfect candidate for that. And so this is the limit as t goes to 0 of. Now, the derivative of the denominator is 1. The derivative of the numerator is 8 to the t times natural log of 8, okay, minus 5 to the t times natural log of 5. All right? Now, we can do direct substitution now. So I'm going to replace t with 0. Now remember, 8 to the 0 equals 5 to the 0 equals 1. Okay? And so this is natural log of 8 minus natural log of 5, which is equal to natural log of 8 divided by 5. So it's a good question. And let's take a look at another one. So let's take a look at example 6. Suppose I ask you the following. Suppose we get the limit as x goes to infinity of, and we'll do this one, x plus x squared divided by 1 minus 2x squared. Now, x plus x squared approaches infinity, and 1 minus 2x squared approaches negative infinity as x goes to infinity. So this is of the form infinity over, we'll say negative infinity, right? And we can apply L'Hopital's rule here. And so by L'Hopital's rule, this is the limit as x goes to infinity of the derivative of the numerator is 1 plus 2x. The derivative of the denominator is negative 4x. And if we do this again, if we're on repeat, we get infinity over negative infinity. And so we can apply L'Hopital's rule yet again. And so, and just incidentally, sometimes you might find that happening. And so this is the limit as x goes to infinity of, we get 2 divided by negative 4. And so the correct answer here is negative 1/2. And so therefore the limit as x goes to infinity of x plus x squared divided by 1 minus 2x squared is equal to negative 1/2. That's how we do number 6, example 6. Let's take a look at another one. So we'll do example 7 here. And so what if I give you the following? So I'll give you this one. The limit as we'll do this. X goes to 0 of, this one's a good one to point out to you guys. Suppose we have the square root of 1 plus 2x minus the square root of 1 minus 4x divided by x. This one's fantastic. And so instead of L'Hopital's rule, which you can technically do here, I would recommend multiplying the numerator and denominator by the conjugate of the numerator. So, in other words, what I'm going to do is multiply the numerator and denominator by the square root of 1 plus 2x plus the square root of 1 minus 4x divided by the square root of 1 plus 2x plus the square root of 1 minus 4x. It's a great way to simplify your work. Because watch what happens here. This is the limit as x goes to 0 of. In the numerator, we get 1 plus 2x minus 1 minus 4x. In the denominator, we get x times the square root of 1 plus 2x plus the square root of 1 minus 4x. Okay? And so this is equal to the limit as x goes to 0 of, we get 1 plus 2x minus 1 plus 4x divided by x times the square root of 1 plus 2x plus the square root of 1 minus 4x. Now, the ones cancel, right? And 2x plus 4x is 6x. So we get the limit as x goes to 0 of, we get 6x in the numerator, we get x times the square root of 1 plus 2x plus the square root of 1 minus 4x. I hope that's okay, because watch what happens. The x's cancel, and if I replace the x with 0, I get 6 over square root of 1 plus 2 times 0 plus the square root of 1 minus 4 times 0, which is equal to 6 over 2, which is equal to 3. Let's take a look at one more example for this video here. Suppose I give you this one. We'll call this example 8. And I'm going to give you this, just to try to give you guys different looks at problems. The limit as x goes to 0 of arc sine x divided by x. This one's really interesting, actually. Now, this is, of course, of the form 0 over 0, okay? Well, let's do that. That's 0 over 0. So we can apply L'Hopital's rule here. So this is the limit as x goes to 0 of. The derivative of the denominator is 1. The derivative of the numerator is 1 over the square root of 1 minus x squared. And so this is 1 over the square root of 1 minus 0 squared, which is equal to 1. And so therefore the limit as x goes to 0 of arc sine x divided by x is equal to 1. So I thought that was pretty interesting. And I want to give you one more. So I think I need to give you one more. So we'll call this example 9. And perhaps maybe I need another video on just lots of examples, because there's a lot of variations on this, and I think you guys need to be exposed to a lot of variations. Now, if I have the limit as x goes to infinity of, and what we're going to do is we're going to do x to the 3 halves times sine of 1 over x. Now, this one's really, really, really interesting, because this is of the form infinity times 0. And infinity times 0 doesn't make any sense whatsoever. So the one thing we have to take note of is the following. So I'm going to write x to the 3 halves as 1 over x to the negative 3 halves. Okay? Now, if x to the 3 halves goes off to infinity as x goes to infinity, x to the negative 3 halves goes off to 0. Okay? And so, in other words, I'm going to write this as the limit as x goes to infinity of sine of 1 over x divided by x to the negative 3 halves. And I claim this is of the form 0 over 0. And we have to understand L'Hopital's rule will apply. So by L'Hopital's rule, this is equal to the limit as x goes to infinity of, we get, by the chain rule, cosine of 1 over x times negative 1 over x squared. That's the derivative of 1 over x with respect to x. In the denominator, we get negative 3 halves x to the negative 5 halves. Now, 1 over negative 3 halves is negative 2/3. So I'm going to pull negative 2/3 out in front of the limit, okay? And I'm going to multiply by the limit as x goes to infinity of. And, well, in fact, we don't even need the fraction bar. So let's get rid of the fraction bar. So I'm going to have x to the 5 halves times cosine of 1 over x times negative 1 over x squared. Now, a negative times a negative is a positive. And so that's going to be 2/3. So we're going to get 2/3 the limit as x goes to infinity of x to the 1/2, right? 5 halves minus 2 is 1/2. Think of the 5 halves as 2.5. 2.5 minus 2 is 0.5. 0.5 is a fraction, is a half. And so this is x to the 1/2 cosine of 1 over x. And so this is infinity. It's a good question. And that's going to do it for this video where we did, it's a lesson on limits, where we did a little bit of L'Hopital's rule and a little bit of simplifying before we take the limit. So, okay, thank you. And it's 9 examples.